Is it visible?
Yes, ma'am.
Yes, ma'am.
So last we stopped with this slide, where we considered the duality between the production and the cost mechanism. So we started with output maximization, and then we introduced the cost minimization, and then we showed that the cost minimization as well as output maximization, these two numerical exercises basically giving us the same second order condition. So starting from one, replacing few matters, we can reach at the second order condition of the other. So we stopped theoretically with these particular slides. So now I'm starting the discussion with short run and the long run cost functions. Short run cost function can be derived using the following system of equations consisting of production function, cost equation, and the equation of expansion path. So already you are familiar with these concepts. So what we did, we considered all the inputs as the variable component, and for that matter, whatever cost equation we have derived using the cost minimization subject to output maximization, our output constraint, that is the long run cost. Okay, that is the long run cost, because we are considering all factors of production are variable. However, to derive the short run cost function, we will follow the similar kind of mechanism. It's not that to derive the short run cost function, we will follow other method. The difference is here, all the factors of production are not variable. So some of the factors will remain fixed. Okay. So that is the idea. This idea we will bring in terms of the plant size. We will consider in the short run, the plant size is given. Whereas in the long run, the firm can choose its plant size of the plant. In the short run, the plant size will be given, whereas in the long run, the firm can choose its own optimum size of the plant. Okay. So we will differentiate between short run and long run in this way in terms of the size of the plant. So if you look at these equations, we start with this production function, we will have this cost function. So apart from R1 x1 plus R2 x2, here I have incorporated a fixed component that first I have written or presented in terms of B. And this is the equation of the expansion path. This is the equation of the expansion path. Actually, first we will write the Lagrange. From the Lagrange, using the first order conditions, we will prepare two equations. First, we will get three equations. However, from three equations, we will reach at two. So actually, we divide equation number 1 by equation number 2 and generate the equation to the expansion path. Okay, so that equation also I'm writing here, the equation of the expansion path, that is here. This system of three equations can be reduced to a single equation in which cost is stated as an explicit function of level of output and input prices plus the cost of fixed inputs. So actually solving this equation, we get x1 star and x2 star. Once we get x1 star and x2 star in terms of R1, R2, the parameters of the model, R1, R2, and in case of cost minimization, we will have Q naught because we will fix the level of output. So the Q will appear as the parameter. So R1, R2, and Q, these three elements will be the parameters of the model in context of cost minimization. So what we are telling, we can solve for these three equations. We can solve three equations, and finally, we can write the cost equation as a function of Q, R1, R2. In terms of the parameters, if I write the cost equation, that will be a function of Q, R1, R2. Remember, we are talking about cost minimization problem, and for that matter, output is a constraint. Output is coming as a constraint. Phi is non-decreasing, homogeneous of degree 1, and concave. This cost function is non-decreasing, homogeneous of degree 1, and concave. Okay, so already in the beginning we discussed some of these properties, and today I'll add a note on homogeneous and homothetic functions as well. Okay, so if anyone have any doubt regarding the notion of homogeneous function, homothetic function, you will get it from the note. The cost equation can further be presented as C as a function of Q only plus B. Okay, C as a function of Q only plus B. Okay, because Q is a function of x1, x2. So in the function form, we can write, okay. So we can write cost as a function of x1, x2 to begin with. And then if I solve the values for x1 and x2, that these are coming in terms of Q, R1, R2. Again, in the production function, if I replace x1 star, x2 star, okay, that will be a function of R1, R2. So, instead of writing Q, R1, R2, we can simply write Q, because ultimately Q is also a function of R1, R2. So this provides the minimum cost of producing the output. This is divided as follows. Sorry, this is derived as follows. Select a point on the expansion path, substitute the corresponding value of the input levels into the production function to obtain the corresponding output level, multiply the input levels by the fixed input prices and obtain the total variable cost for these output level. Finally, add the fixed cost. Okay, already you did all these things, though I have written these steps like this, apart from the last step, that is add the fixed cost component. Apart from the last step, you did all these things. You have presented the Lagrangian expression for cost minimization, bringing the objective function as well as the constraint, solved those equations, got the values of x1 star and x2 star, putting those values in the original cost equation, you got the actual or the cost function at the optimum. So all these things you already did. The new thing in terms of short run cost function is you have to add the fixed cost component. That's all. Okay. Solution of x1, x2, all these things in terms of R1, R2, all these things are similar. Let the levels of entrepreneurs' fixed inputs be represented by a parameter K, which gives the size of his plant. What I mentioned, we will differentiate between short run and long run, introducing the size of the plant. Already in your microeconomics course in the last semester, you learned something about the size of the plant, in the short run, because some of the factors of production are fixed. The firms face a particular plant size. In the long run, the firm can select the optimum plant size depending on the market demand for the commodity. Okay, so I think you have idea about this. In the short run, the size of the plant is fixed, whereas in the long run, the firm can choose the optimum plant size. Am I right? Can you remember this point?
Yes, ma'am.
Yes, ma'am.
Okay. The entrepreneur's short-run problems concern the optimum utilization of a typical plant size. This is the size of the plant and you have to optimally utilize it. So actually what the plant does consider the SAC, short run average cost, and will like to produce at the minimum of this SAC. If you consider a particular short run, the firm's objective will be to produce at the minimum point of the SAC. So that will be the objective, optimally utilize the plant size. In the long run, entrepreneur is free to vary K and select a plant of optimum size. Once he selects the value of K, he is faced with the conventional short-run optimization problem. Considering K to be continuously variable system of equations consisting of production function, cost equation, and equation of expansion path can be presented as follows. Q is a function of x1, x2, k. Okay, I'm considering k to be continuously variable. Okay, so there are different possible plant sizes that we are considering. So in the output function, we are bringing k. So f of x1, x2, k. So the cost equation will be replaced by R1 x1 plus R2 x2 plus a function of k, psi of k. Your cost will depend on what is the size of your plant. Cost is a function of size of the plant too. C is a function of x1, x2, that is two inputs, as well as the size of the plant. And we will consider phi prime k to be positive. That is, fixed cost is an increasing function of plant size. Okay, if you select a bigger plant size, in that case, your cost will be higher. Fixed cost component will be higher. So phi k is appearing here as the fixed cost component. You are selecting, you have different options in the long run, and from those options you are selecting one, and when you are selecting one, actually we are talking about short run. When you have a basket of options, you are at long run. When you are selecting one, you are at short run. That selected plant will give you the fixed cost of production. Size of the plant will determine what will be the electricity bill, what will be the maintenance charge, what will be the tax for this or that, So we are clubbing all these matters which are based on the size of the plant, and we are considering this as a fixed component for a particular short run. However, in the long run, you have options. And whenever you are selecting something, you are at a particular short run. This is the idea. Now, the expansion path, that is also a function of x1, x2, and k. So, k we are bringing in our model, and we are considering that k is continuously variable. However, when you are selecting or picking and choosing a particular plant size, then the plant size is a given factor to you, and that will appear as a fixed cost component. That will appear as a fixed cost component. So fixed cost is an increasing function of plant size, as I mentioned. That is, we consider psi prime k to be positive. The shapes of the isoquants, isocost lines, and expansion path depend on the value of the parameter k. You will find that in all three equations, Q, C, and the equation to the expansion path, we are bringing the component k, the size of the plant. So, all three things, isoquants, isocost lines, and expansion path depend on the value of the parameter k. Generally, two of these three equations are used to calculate x1 and x2, and total cost may be expressed as a function of output level and plant size. Okay, You know the method of solving this thing. So I'm not focusing on these sentence, because you know how to maximize output subject to cost constraint. You know how to minimize cost subject to output constraint. So all this mechanism is already done. So you know the process by which we derive the input demands and we plug these things in the cost equation, get the minimized cost, or in output equation get the maximum output. So you know these steps. So finally what we are telling that the cost equation can be presented in terms of Q and K. So first I mentioned it is a function of Q like this, and now along with Q we are bringing another factor K. Okay, already K we have incorporated in our analysis. So it may be expressed as a function of output level and plant size, QK, plus psi K. This describes a family of total cost curves generated by assigning different values to parameter K. As soon as plant size is assigned a particular value K is equal to K naught, equation 3 becomes equivalent to equation 2 and the short run analysis is applicable. So what we are telling that as long as C is a function of QK plus psi K is there, it is a long run cost function because K is continuously variable. However, if a firm selects a particular plant size, that is K is equal to K naught, then equation 3 will be rewritten just like equation 2. C will be a function of Q only. C will be a function of Q only. Okay, function of Q only. Okay, and there will be a fixed component. Psi K will be a fixed amount, a fixed cost of running that particular plant size K naught. So equation 3 becomes equivalent to equation 2 and we will go for the short run analysis. So just a little difference is there. As long as C is a function of output and the plant size, it is a long run cost. And whenever K is replaced by a fixed number, say K naught, it is becoming a short run cost. I'm repeating, as long as you have option to select different values of K, alternatively, as long as C is a function of output and the plant size, it is a long run cost. However, if you select a particular option, particular value of K, it will become a short run total cost function. Okay, so just this difference is there. Just this difference is there. A variable component, you have in your hand. When you are fixing that value of the variable component, it is becoming short run analysis. The long run total cost function gives the minimum cost of producing each output level if the firm is free to vary the size of the plant. More specifically, for a given level of output, the firm computes the total cost for each possible plant size and selects the plant for which the total cost is minimum. Here you have multiple options, 1, 2, 3, 4, 5, 6. If there are 50 possible plant sizes, all 50 options are with you. And then you are selecting, suppose you want to produce 10 tons, for 10 tons, you have 50 possible plant size. You are selecting one which will give you the minimum cost. Now you want to produce 12 tons, say. You are selecting the plant which is giving you the minimum cost. Now finally you want to produce say 100 tons. In that case, it may happen that the first plant size or the second plant size will give you the higher cost. if you go for a bigger plant size, in that case it will be beneficial. So it may happen when your scale is lesser, in that case a particular plant size will be optimum for you. If your scale, that is output, is very high, in that case you need another size of the plant. If you like to produce a huge amount using a smaller plant size, in that case cost will increase. Okay, alternatively, if you want to produce smaller output using a very big plant size, in that case also the production cost will increase. So there is an optimum size of the plant with respect to each level of output. Okay, there will be an optimum size of the plant with respect to each level of output. So, in the long run, you have option to select anyone. In the short run, whenever you are selecting one, we are specifically talking about a short run. Graphically, the thing will be easier to understand. Look at this graph, we are measuring output along the horizontal axis and we are measuring cost along the vertical axis. Measuring output along the horizontal axis and measuring cost along the vertical axis. Okay, and we'll like to place 3 plant sizes. We will like to consider 3 possible plant sizes to produce a particular level of output. To produce a particular level of output, say OR, we are considering 3 possible plant sizes, K1, K2 and K3. First, we are drawing the total cost with respect to K1, then total cost curve with respect to K2 and total cost curve with respect to K3. Okay. Now, if I like to produce OR, let me check whether I can draw that. No, it will be not possible. If I like to, produce OR with the plant 1, this will be, S will correspond to the total cost. The point S will correspond to the total cost. However, if I like to produce the same amount using the second plant size, the cost will be given by this perpendicular, which is dropped from T to the vertical axis. Finally, if I like to use the third plant, the cost will be RU. So, to produce OR, if I use plant 1, my cost will be RS. If I use the second plant, it will be RT. And if I use the third plant, it will be RU. So, which plant I'll select? Anyone? Which plant I'll select? 1, 2 or 3?
Ma'am, ST.
1.
ST মানে এটা বুঝলাম না। 1. We will select plant
RS.
RS. দেখো একটা কস্ট হচ্ছে RS, সেকেন্ডটা কস্ট হচ্ছে RT, থার্ডটার কস্ট হচ্ছে RU. And always your objective is to minimize the cost given the specific level of output. So which plant will be profitable?
Ma'am, RS.
RS. That means the first plant will be profitable. You are
Yes.
হচ্ছে বলো? You are the highest cost. I'm measuring cost along the vertical axis. So UR is the highest cost. So we should not go for this. If I can produce OR using, or where the cost is only RS, So if I can produce OR with the cost RS, definitely I'll select plant 1. Why should I go for plant 2, which will bring some additional cost of the amount ST? Or why should I go for third plant, which will bring an additional cost of SU? Okay, so I'll select only plant 1. If my target output is OR, if my constraint is OR, I'll select plant 1 because that is minimizing the total cost of production. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So let me draw this diagram here. So first I talked about an output level like this. Okay. So along this axis we measure Q, along this axis we measure C, and we talked about OR level of output, S, T, and U. Now suppose I like to produce an output level given by, say, this level. Suppose it is V. So I like to produce OV. Okay. Now, if I like to produce OV with the, I can extend the plant size for first plant. Like this. So, to produce OV with plant 1, I'm facing the cost this much, up to this much. So up to this much, I'll face the cost. So suppose it is L. Suppose this is M. And suppose this is N. Okay. So which plant will be best for me? Most cost effective to produce
Second
OV?
plant.
Second plant.
Okay. Now still, if I continue with the first plant, my cost will be highest. That is VL. That will be highest. Okay. However, if I use the second plant, it will be VM. This is the least. And if I use the third plant size, it will be Vn, which is bit higher than Vm. So for me, the second plant will be most profitable. Finally, if I like to produce, say, output level given by this one, say. I mean, this is the output level. And if I extend and red will cut, somewhere here, which will be not possible to draw in this board. And I hope you are understanding, if you extend this plant size somewhere here, it will intersect with this output level. Now for this particular level of output, say OZ, which plant will be optimum?
The third one.
Third one. Okay, third one is giving the minimum cost. Third one is giving the cost, say, ZP. Okay. Suppose this is the cost. This is the minimum cost. If you use the second plan, the cost will be higher. And if you use the first plan, the cost will be highest. Okay. So for each particular output level, there is a specific plant size which will give you the minimum cost, Now, long run analysis tells us, we are considering different level of outputs, OR, OV, OZ, and trying to find out which plant is giving me the best position. So long run indicates that one. Now, one is 1 or plant size 2. For producing the level of output OR, I am selecting plant size 1. Once I do this, I am talking about the short run. For the output level OV, the second plant is the best one. So once I select for OV level of output, the second plant, I am now in a particular short run. For the OZ level of output, ZP is the minimum cost, or the plant 3 is giving me the minimum cost. So once I understand for OZ, I have to use this plant size, then the cost I have to bear for this plant size is coming as a fixed cost. So essentially, I am going for the short run analysis. So whenever I'm picking a particular plant size among many, I am in a short run. And when I am selecting from many, that discussion essentially relates me to the long run. Now, joining these points, say S, M, P, we will be able to draw the long run curve. Joining the points S, M, P, where the output level is cutting a plant size and giving the minimum cost. Joining these points, we can draw a continuous locus, we can derive a continuous locus, and that locus will give me the long run curve. So the long run curve can be like this, just look at the diagram I'll draw. That will be not a good one. So please go back to the slide and we check the thing, this will be like this. This will be like this, the dotted line. So this roughly this line, roughly this line, will give you the long run total cost curve, long run total cost curve. Okay. Every short run total cost curve has a point of tangency with a long run total cost curve. Every short run total cost curve has a point of tangency with the long run total cost curve. And for that matter, the long run total cost curve is basically enveloping a number of short run total cost curves. Since every short run total cost curve has a point of tangency with the long run total cost curve, therefore, long run total cost curve is enveloping all the short run total cost curves. So the long run total cost curve can be called an envelope curve. Long run total cost curve can be treated as an envelope curve. Okay, so, here you will get the write-up. This process is repeated for every output level, and the long run cost curve is defined as a locus of minimum cost points, locus of minimum cost points. The long run cost curve is the envelope of the short run curves. It touches each and intersects none. So first tell me whether you are understanding this issue and how we are reaching at the long run total cost curve from the short run total cost curves. How we are reaching at the idea that long run total cost curve will envelop the short run total cost curves. Any question? Any part I need to repeat? Is it okay to all of you?
Yes, ma'am.
Okay, so equation 3, this equation 3, which is the long run cost, long run total cost curve, C as a function of QK plus psi K, which is a function of the variable plant size, that indicates a family of short run cost function, or in other words, a long run cost function indicates a family of short run cost functions. So equation 3, the family of short run cost functions can be rewritten in implicit form as C minus phi of QK minus psi K. If the equation was C equal to, so I'm bringing all the terms to the left. C minus phi of QK minus psi K is equal to another function, a function G, which is a function of CQK is equal to 0, which is a function G of CQK is equal to 0. For every plant size, there will be a typical C. For every Q, there will be a typical K, and for that typical K, we will have a typical C. So G is a function of C, Q, and K, and that we are setting to be equal to 0. Set the partial derivatives of equation 4 with respect to K equal to 0. So, suppose we will like to find out the optimum plant size. So what we will do, we will consider del G by del K. Considering C and Q are constants, considering C and Q are constants, to find out a particular plant size, we will take the partial derivative of G with respect to K and set this equal to 0. The equation of the envelope curve or the long run cost curve is obtained by eliminating K from equation 3 and 4 and solving for C as a function of Q only. as a function of Q only. So this is the equation for the long run, G of CQK. And if I consider the short run, it is C minus phi K is equal to 0. C minus phi K Q is equal to 0. Long run total cost is a function of output level given the condition that each output level is produced in a plant of optimum size, that is using the appropriate short run cost function. Long run total cost is a function of output level given the condition that each output level is produced in a plant of optimum size, that is using the appropriate short run cost function. So when I am enveloping, I am for a particular level of output, I am looking at which plant will give me the minimum cost. Accordingly, I am selecting and deriving the long run cost function. Okay, so this is the meaning of the last sentence. Long run total cost is a function of output level given the condition that each output level is produced in a plant of optimum size. Since K is assumed to be continuously variable, the long run cost curve has one and only one point in common at the point of tangency with each of the infinite number of short run cost curves. So K is continuously variable, in the short run. When we are selecting a particular level of output, we are selecting a particular plant size as well. So at that point only, the long run total cost will be similar to that of the short run total cost. For that particular plant size, the long run total cost will be exactly equal to that short run total cost. However, if the output level OR changes only in the neighborhood, there will be another point which will be more profitable, or there will be another plant size which will be more profitable. Now, what I am trying to tell you, for the output level OR, RS is the minimum cost, or K1 is the best plant size. This is the best plant size. However, if output changes only in the neighborhood, output changes in the neighborhood, plus minus something. We have a number of cost curves. Here I have selected or presented 3, and for that matter, we are getting like this. However, we have a plant size, we can draw a graph like this. Okay, so this plant, this one, will be best for if the output is bit less compared to OR. In that case, again, there is a plant, and that plant is giving the minimum cost, the maroon one, that is giving the minimum cost, not the red one, not the K1. Suppose it is K0. So this size is giving the optimum cost, So only at the point, when you are, for a particular level of output, you are selecting a particular plant, at that point only, the short run cost and the long run cost will be similar. Okay. So only at the point of tangency, the short run total cost and the long run total cost are similar. For rest of the points, the cost will vary, because for every level of output, there is a different plant size which is optimum. For every level of output, there is a different plant size which is optimum. Not a particular plant size will be optimum for two different levels of output. Okay. Remember that in the long run, K is continuously variable. K is continuously variable. Okay, so we can generate infinite number of short run cost curve indicating the size of the plant. Okay, so this is all about the envelope curve in terms of total cost. We can discuss the similar issue in terms of average cost as well, because average cost is nothing but total cost divided by level of output. So all the properties will be retained. All the properties will be retained in the average cost function. All the properties will be retained in the average cost function. Just you are scaling it with respect to the output, So you are trying to find out per unit cost. In the total cost, it is the entire cost, and then you are interested in per units cost. Okay, so it is the matter of scale only, scaling the component. So all the properties of the total cost will be retained in the average cost function. So since average cost equals to total cost divided by the output level, the minimum average cost of producing a particular level of output is attained at the same plant size as minimum total cost of producing that output level. The long run average cost curve can be derived by constructing an envelope of the short run average cost curves. However, you know this thing, LMC is not an envelope of SMCs, because LMC is a different thing. This is related to change. Okay, change in total cost due to change in output. Average cost is just a matter of scaling. However, the marginal cost is a different concept. Okay, it is about change in the thing. And all of you are aware of these diagram, the long run average cost curve. So if I consider three plant sizes, three short run average cost curves correspond to those three plant sizes, and in the falling part of the LAC, only a falling SSC will be tangent. At the minimum point of the SSC will be tangent. In the rising part of the SSC will be tangent. So do you know all these things?
Yes, ma'am.
Falling part, rising part, minimum point, you know these things very well? Rest of the students?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Don't draw this kind of diagram, okay? Don't draw the kind of diagram like this, Don't draw this kind of diagram. This is a wrong one. Okay? Sorry. Only here the minimum point will coincide, and here the tangent will occur in the rising part. Okay, so anyone, would you tell me why this is happening? Why the first diagram is a wrong one? It's not covering the minimum of all these points. In case of total cost, it is covering the minimum cost of producing this output. Whereas when we are drawing the average cost curve, why in the falling part of LAC, it is tangent with the falling part of the SSE, and so on. You told me you know the matter. Anyone? Please tell me. Udita, can you tell me? Please try. Shomadrita? Konkona? Kritika?
Ma'am, what I am thinking is that since till a particular point, the slope of LSE is negative, so therefore the point of tangency also, the shape of SSE must also be negative. And with that reasoning, in the rising portion also it should be positive and so on.
Yeah, that is the only reason,
Yes.
You told me you know about the diagram, etc. That is the answer, Very good. A falling curve can be a tangent only in the falling part. A rising curve can be create a tangency with the rising part. When we are considering the total cost curve, this problem is not appearing because the curves are increasing. So, all the curves are increasing, so there is no problem. However, in context of average cost curve, when we are considering these different plant sizes, uh, the negative slope of the long run average cost can create a tangency only with the negative slope of short run average cost. Only at the minimum of LSE, it will be tangent with the minimum of SSE. In the rising part, it will be tangent with the rising part. So that's the answer. So there is the simple mathematics in it. The rising curve will create a tangency only with a rising curve. Okay, only the two positively sloped curve can make a tangent, two negatively sloped curve can make a tangent, and when the slope is zero, for one curve, the other curve which is tangent for that too, we need a zero slope. So that's the answer. There is simple mathematics behind this, nothing else. Okay, so this is all about, how we can present the idea of envelope curve using in context of cost minimization exercise. How we can present the long run cost, short run cost, long run total cost, enveloping the short run total cost, long run average cost, enveloping the short run average cost. So is there anything which I need to repeat once again, or any clarification do you need for any portion? Anyone?
Ma'am, can you show the previous slide once?
This one?
Yes, ma'am.
Anyone? Any question?
I have one question. Like when we are choosing this firm, like once it is the firm is set or chosen, then it is short run. And
Yes.
in the process, like when we have different firms and we yeah, we are in the process, then it is a long run.
Yes. As long as K is continuously variable, it's a long run. Okay. And when, at this moment, on the date of 21st of June, I am selecting a plant size to produce my output. In that case, it is a short run. I'm fixing the factor. Whenever, you are fixing the plunge size, it is a short run. Okay.
Yes.
And when there are options, it is long run. Okay. So, before coming to the class, logging for this class, you have multiple options for using this time. So for coming 1.5 hours, 2 hours, you have multiple options. And now you are in front of laptop. In laptop only there are, or phone, there are thousands and thousands of options. Okay. So you can go for cooking class, you can go for movies, you can go for economics class, you can go for anything you like. So, it's in that case, we cannot call it a short run. Whenever you are in the class, you are doing something, you are fixing the utilization of the time, it's a short run. Okay, so among many options, when we are picking and choosing, we are fixing several matters, it is a short run. Okay. Now, in bigger sense, at this moment you are doing economics honors, economics major. So it is a short span in your entire educational span. Okay, so this is a short run. Okay, however, when you will, after the graduation, when you will have number of options, that will be the long run. Among variable things, you will have to select, we can choose something. Okay, so this is the idea. When you are picking and choosing, fixing something, that is short run. When all the variable components are in front of you, that is a long run. Upanita, is it okay?
Yes, ma'am. Thank you.
Okay, on the basis of that, these concepts, we can develop the envelope theorem too. However, today I'll not discuss this envelope theorem. It may be a bit difficult. Let's first grasp all these ideas first, and then I'll discuss the envelope theorem. So today I'll not discuss the envelope theorem. However, what I mentioned, I'll go for some comparative static results. However, before going to comparative static results, or you know, discussing some derivations on the basis of the optimum value function, let's discuss a note on homogeneous and homothetic function. So all of you did this thing in first semester. However, just as a note, please add these things so that you understand these are also the part of the syllabus. There may be some question on, as we discussed in context of utility function, show that the utility function is homogeneous of degree 0. In case of cost function, the question may be show that the cost function is homogeneous of degree 1. Okay, so whatever you learned earlier, those are coming as part. So all these things should be with you. Actually, sometimes, as I mentioned last day, depending on the nature of course, we are learning something first which should come later, and we are learning something later which should come first, because everything has been divided into few semester. Okay, so therefore all these things will continuously happen at least up to second year. For the first 4 semesters this happened. So your task is to integrate the matters. I hope now you understood. First, actually using the Lagrangian process, we will derive the demand function, and then we will discuss the properties of the demand functions. We will discuss about elasticities, etc. However, mathematically, derivation of elasticity, etc. are easier concepts, and that we do as part of microeconomics, part of mathematical economics, etc. Okay. However, if you look at the steps, elasticity discussion should come later. The bordered Hessian determinant based discussion will come first. So all these things are there. So once again, take a note. Take a note. Give heading homogeneous and homothetic function. Homothetic production function. Homogeneous and homothetic production function. A function f of x1, x2 to xn, which has written in the board, a function f of x1, x2 to xn is homogeneous of degree r, is homogeneous of degree r if when all inputs are increased or decreased, when all inputs are increased or decreased by the same proportion, all inputs are increased or decreased by the same proportion, output increases or decreases by rth power of that increase. Output increases or decreases by rth power of that increase. Thus, f is homogeneous of degree r. Thus, f is homogeneous of degree r if f of within bracket tx1 up to txn is equal to t to the power r f of x1, x2 to xn. This line, this line in the board. F is homogeneous of degree r if f of t x1, t x2, etc. up to t xn is equal to t to the power r f of x1, x2 to xn. Or if I of tx1 up to txn, that is del f by del x1, say, fi of tx1 up to txn divided by fj as a function of tx1 up to txn is equal to fi of x1, x2 to xn divided by fj of x1, x2 to xn. That is the partial derivative of f with respect to one input divided by partial derivative of f with respect to another input is equal to fi by fj as a function of x1, x2 to xn. This implies slopes of the level curves are the same. This implies slopes of the level curves, that is isoquant here, same along every point of, slopes of the level curves are the same along every point of the given ray out of the origin. Given ray out of the origin. Okay, so if you draw the isocost lines, this will be parallel. If you draw the isoquants, you know, this will be almost parallel to each other. Okay, so if you consider the expansion path or draw a straight line passing through origin, the slopes of the level curves you are considering, that will be parallel to each other. Fi by fj, if you increase isoquant level by, you know, t, that will be similar to that of Fi by Fj. Okay, that will be similar to that of Fi by Fj. So it doesn't matter if you increase all the inputs and you know, consider a different level of the isoquant, the slope will be same. The slope will be same. The lines will be parallel to each other. And returns to scale is increasing. Returns to scale is increasing if r greater than 1, decreasing if r less than 1, and constant if r is equal to 1. So this is the homogeneous function paragraph. The class of functions, look at this underlined line. The class of functions y is equal to capital H of x1, x2 to xn is equal to capital F of small f of x1, x2 to xn where f not equal to 0 and small f of x1, x2 to xn is a homogeneous function, is called the homothetic function, and no generality is lost. No generality is lost if small f is of homogeneous of degree 1. Add one more sentence. If a production function is homogeneous of degree 1, then marginal products are homogeneous of degree 0. Then marginal products are homogeneous of degree 0. Okay. Then from Henderson and Quant, please check this homogeneous property, homothetic property of Cobb-Douglas type production function and CES production function. Cobb-Douglas type production function and CES production function. For Cobb-Douglas production function, for CES production function, check their homogeneity, check the homogeneity of their marginal functions. Okay. check whether the functions are homothetic in nature. So please go through those sections where there is discussion on homogeneous production function, homothetic production function, etc. Maybe in your earlier semester you did all these things. However, these points you should always keep in your mind. All these things are very, very important when we are going for constraint optimization, etc. There may be a small question based on homogeneous property, homothetic property, etc. So, you have to integrate all the concepts, so clarification of these concepts are needed. Any question? Do anyone have any question regarding these ideas, homogeneous function, homothetic function, or anything? Any question? Okay, I'm repetitively telling that we do not have much time for revision, because, I like to complete the syllabus tomorrow if possible. If it is impossible, day after tomorrow. Okay, I'll not do the new things beyond that. However, if some student has some problem, already a few students told me about, clarifying the notions of convexity, concavity, etc. So, I'll ask for the names who will like to join the classes, or who are the students who need the clarification regarding all these things. However, we do not have much time for going for a number of revision classes, etc. Because, after this week, I think you have GE exam on 29th. Am I right? And you have AECC too.
Yes, ma'am. 28.
Yes, 28 and 30.
Yeah. So you have ACCG, etc. So, so it will be best if we can complete the syllabus, by this week, by tomorrow or day after, by Friday, latest by Friday, we have to complete everything. After that, whatever we will do, that will be the revision based, or if you have some, if you need some clarificatory classes, we will go for that. And your main exam will start from 15th. Okay, so you need some time to go through the things and revise all the things, prepare your own notes. So you also need some time to do these things. And regarding the style of exam, I am just repeating, I mentioned it in the last class as well. So some part will be based on the time bound written thing, and some part will be viva based, and during the viva maybe will be asked to solve some numerical exercises, etc. As you did, I hope by this time you are tuned with this matter. Already you gave your internal assessment, where when some of you did some exercises. So that may be the numerical exercise, that may be the theoretical exercise. So there may be this kind of thing. Okay, so during the viva, then also you may need to derive something, and in the written part, naturally you have to write the matters. Okay, just very briefly, let's start comparative static results. So comparative static results related to the cost minimization problem. So we are considering the Lagrangian expression. You are familiar with this expression, W1 x1 plus W2 x2. Here the price of x1 is W1, whereas price of x2 is W2. Output is considered as Y. Y is the output level. So subject to the output constraint, we are trying to minimize the cost. The required Lagrangian is given by L is equal to W1 x1 plus W2 x2 plus lambda into output minus f of x1, x2, where lambda is the Lagrange multiplier. Differentiating L with respect to x1 and x2, you will be able to generate this first order conditions and the second order requirement. is given by this. Already we did all these things, so you are familiar with these states. Solving the first order conditions, we get the optimum input demand functions and the Lagrangian multiplier given by x1, x2, which are functions of the parameters of the model. Okay, these are functions of W1. Sorry. These are functions of W1, W2, and the output level Y. So all three elements, x1, x2, and lambda, are functions of this. Now what we have to do, we have to derive del xi star by del wj. Okay, so what is happening when we are telling that you may derive del x1 by del w1, del x1 by del w2, and you will be also able to derive del x1 by del y, that kind of thing. Similarly, actually del xi star, del wj is taking care of changes in x1 and x2 in terms of w1, w2, own price, cross price, everything. Okay. So both I and j are running from 1 to 2. We may be also interested in the fact that how input demand will change when output changes. That is del xi star by del y. What will be the impact of change in output on input demand? That kind of thing. With respect to lambda, we can take derivative of del lambda star by del wy. That is del lambda star by del w1 and del lambda star by del w2. And we can also derive del lambda by del y. So all these derivatives we need to do. We need to discuss about all these derivatives. Okay. When we will consider x1, x2, w1, w2, there will be 4 derivatives. From the second one, that is del xi star by del y, 2 possible derivatives, del x1 with respect to change in y, del x2 with respect to change in y. So first 4, then 2, 6. And then with respect to lambda, we can find a derivative with respect to w1, w2. So 2 derivatives are there. So 6 plus 2, 8. And we can take derivative of lambda with respect to y. That will be the 9th one. So 9 possible comparative statics we can discuss. So up to this, any question?
Ma'am, if possible, can we leave today's discussion to here?
I didn't get you. আরেকবার বলো তো কি বলছো? What you are telling?
Ma'am, she was telling to stop here.
Please bit louder. You are not audible. I could not hear her. Anyone?
Ma'am, she was telling to stop here.
Okay. He's telling to stop here. Okay. Okay, yeah, I'll stop. Definitely, I'll stop here. I'm just telling these are the derivatives you need to derive. We will derive all these things tomorrow. Yes, I'll derive all these things tomorrow. And with that, I'll, the left out part of the envelope theorem that I'll try to discuss.
Ma'am, are these things available in Hoy's book?
Just a minute. Yeah, in some form or other.